Hello and welcome to the Lab 1 overview video. I have good news and bad news. So the good news is that this lab will take you less than 50 lines of code to complete and get full credit. The bad news is that it will take a lot of thought to come up with those 50 lines of code. So definitely start early. That is my recommendation. But it's going to be a very cool result, I can promise you that. So here's what the lab is going to revolve around. It's the idea of satisfiability, and that's very close to what we've been learning in class. It's like the programming equivalent, almost. So we've been working with logic and logical formulas. Here's one, for example. Another name for this logical formula is a Boolean expression, because like you got these variables and you're doing stuff with them, ands and ors and nots and things, and all the variables involved can be true or false. They're Boolean things, and it's an expression of Boolean variables and Boolean operations, okay? And so for one reason or another, you might make one of these, and you might want to know, like, is there a way to make this expression give back true? And there's a fancy term for that. It's called satisfiable. A Boolean expression is satisfiable if you can give values to these variables in some way and get back true. So this is a satisfiable formula because there's at least one way to make this work. There's a very easy way, just like try them all, just make them all true. If you set p to true, and you set q to true, and you also set r to true. Do you see how that's going to make the whole darn thing true? True, because, I mean, the not r won't help, but p and q makes true, and then you're oring that, and so it all works out. So that is called, this is a witness that it is a satisfiable formula, and so we call this a satisfying solution. And you'll have to wait till upper division computer science to know how useful this idea is, but making programs that do this kind of thing, it's called satisfiability checking or writing a satisfiability checker. It's really useful for a bunch of different things in computer science, like checking if a program is correct, analyzing a program to see what kind of properties it has. Even compilers do satisfiability checking, because like say you have an if statement. Inside of your if statement's condition is some Boolean expression, and if the compiler can prove that it's unsatisfiable, then it doesn't need to compile the body because it will never run. See that? That's kind of cool. So that's satisfiability, and we're going to write a satisfiability solver, or for short, it's called a SAT solver. Okay? So to get there, there's a lot of stuff for this lab, and let's talk about some CSCI 41 concepts, some like object-oriented programming stuff, and then also some memory management stuff that we need to remember to make it work. So in 41, you were forced to manage a lot of memory, right? You did a lot of news and deletes and made stuff on the heap. There is something called a smart pointer. There's a few types in the memory header for C++. This memory header right here. If you include that, you get access to some things that call new and delete for you automatically. So you don't have to worry about it anymore. So even if you haven't learned this yet, it's just what you know, but better, because you don't have to like figure out when to delete your memory. It'll just do it for you. So a smart pointer is like an object that wraps around something on the heap, and it will call new for you, and it will also call delete for you, and everything else is overloaded. Like you can use dereference, you can use arrow, it all works out. Okay, so there's two main types in this memory header that we're going to care about. The first is going to get us ready for the second one. So here's the memory header, and there are a couple types here that we like manage pointers. So unique pointer, that's a pointer on the heap that is unique, and a shared pointer is a pointer on the heap that is shared a bunch of places with other people. So it's shared around, and so we're going to use the second one, the shared pointer thing, in this lab. All right, and there are some ways to make unique pointers and make shared pointers. Okay, so that's what's going on here. So, but really, when you make values of these types, they're really just wrappers around t stars at the end of the day. Like it's a t star that's on the heap being made for you. So you make a unique pointer, it's a t on the heap that's owned by you and only you. It's unique. Okay? So to make a unique pointer, for example, it's essentially like saying new t. It's templated, and so you say there's a make unique function, you call that, and you give constructor arguments, and it will build that t for you on the heap. Okay? And because it's unique, it can't be owned by anybody else. So I have some examples for that, but this is not something that will be in your lab. Only shared pointers. All right. But here is, let me comment out the shared pointer stuff. Here is the idea. So include the memory header. If you say this, I'm going to make a unique pointer to an int, call it p, and I'm going to make it like this. So there's a make unique function, and you can give it constructor parameters. And so this is setting an int to 42 on the heap, and p holds its pointer. So essentially, unique pointer of an int is pretty much int star. It's just wrapping around an int star for you somehow. And all the things are overridden, and so you can say star p. And then I also make this silly example class that has an overloaded destructor, so we can see when it runs. And here's like p2, it's making a brand new C on the heap for me, and it's going to delete it whenever everything is over with. Okay, so the first thing I want to show you is just that it works. So G++, smart pointers, -o, smart pointers. Boop. And so it's printing 42. It works out just fine. It's on the heap. And then also, this destructor for p2 is being called for us, even though we're not saying delete anywhere. It notices when things are done. All right, so let's read this first. So the pointers inside p and p2 are getting deleted automatically for us right before main returns. Like this closing brace right here is when the scope goes away, and we know, or C++ knows that p and p2 no longer are needed. And so it deletes it for you in the destructor. Isn't that cool? So you can pass things around on the heap, and you don't have to worry about it. The one thing you can't do with a unique pointer is copy it to somebody else. You cannot take p2's address and like put it in another unique pointer because it's supposed to be unique. So this won't even compile because this is essentially a copy constructor call, and the copy constructor of unique pointers was deleted. You're not able to use it. So that gives you some very strong guarantees about like how many people are pointing to this place on the heap right now. It's guaranteed to only be one. Okay. You can move it around though. There's a move function in the utility header. If you'd like to look into that, it'll force one of the other ones. Like if you move it, it'll force the other one to be null. And so really only one person still has that address. So that's unique pointers. Feel free to look more into that. But I wanted to show you that so that I can get into shared pointers because that's going to be used in the lab. So a shared pointer is again a wrapper around a T-star. It's holding on to a T-star, but it's not, it doesn't have to be unique. Like you can hold this address in a bunch of different shared pointers, the same place. And so it's a pointer to a T on the heap that can be shared among multiple people. And just like for make unique, there is a make shared function that you can look into on this page if you'd like, where you just call constructor arguments for T, and it will build that T for you on the heap. Okay? And it's just keeping track of like how many shared pointers to that address are there in the world. And once the last one goes away, it deletes the memory. Okay, so here is an example of a shared pointer to an int. So again, this is like an int star, p3, and it's holding 43 on the heap, an int on the heap. So essentially, more or less, that line was this. It's wrapping around this idea, and it's going to call delete for us eventually. So all the things are overloaded, like the dereference operation. And the beauty of shared pointers is you can copy over, and you can have multiple shared pointers pointing to the same place on the heap. So here I am making a C on the heap again, calling it p4, and p5 can hold on to that address. I can use them both because they're interlinked. Like I can set the X field because this C class has an X member variable. I can set that field through P5, and I can print it out through P4 because they're pointing to the same place. Okay. So that's glorious. And so I see the 44, well, the 43 first printed, and then the 44 printed here. Okay. And then also, the shared pointer is keeping track of like how many people are pointing to this place on the heap. The C that we make here, P4 has a pointer to it and P5 has a pointer to it. And then at the end of the scope again, once they both go away, once P4 goes away and P5 goes away, there's no one to point to this C on the heap anymore. And so it automatically calls the destructor for you. It just keeps track of how many people are holding on to it. Right? Once everybody's done, it gets deleted, and it's beautiful like that. Okay, so that's smart pointers, and we're going to be using shared pointers in this lab. It's honestly, just think of it as a T-star. Think of the shared pointer to a T as a T-star on the heap. It's just you don't have to worry about it. It's going to call delete for you. You'll never leak memory if you do it right. Okay, so that's pretty cool. Next thing I want to review is inheritance. This is definitely a 41 topic. So let's go over that silly example that is very common where like you have cats and dogs. So every cat and dog is an animal, right? So usually if you make a class that represents cats and a class that represents dogs, you want them to inherit from the animal class, and that's where you'll put all the common properties of a cat and a dog. You have their animal qualities living up there. All right, so like maybe every animal has a name, and has like a talk method. Every animal knows how to make some kind of noise, and then maybe like getters and setters for that name. You just put all that stuff up in the base class, because animal is the thing that's going to be inherited from, and it'll be copied into the subclasses. So that's the idea. So we notice that we need inheritance when we have an is-a relationship. A cat is an animal, a dog is an animal. They should all have names and be able to like reset them and get them back, and they should all have talk methods. And so we're going to place that in one spot so that we don't have to reinvent the wheel. It's called our base class, among other things. Base class. And cat and dog are subclasses. Subclass. Okay, so those are those. And inheritance allows you to reuse code, and it models this idea of something being something else. So like in the cat class, maybe what you'll do is you will override that talk method. Override the talk method to say cat noises like meow, and you'll override the talk method in the dog class as well to say woof, because that's what should happen. Okay, so that's inheritance, and here's my silly example of that. Boop. So again, we have an animal class that's going to be derived from. So what does an animal have? It has a name, member variable, which gets set in the constructor. It has a getter for the name. Let's pretend that you can't set the name, just make it easy on ourselves. And then it has a talk method that can be overloaded and applies to, like it'll pick the correct one if you use it from the perspective of an animal, if you make it virtual. So this is a virtual method, so it'll always pick the correct one, and it's going to have no implementation in the base class. This creates a pure virtual function, which creates animal as an abstract class. You cannot make any animal objects in main now, because there is a function without any implementation. So this is kind of going to force every single animal subclass to implement, give a concrete implementation for this talk method if you actually want to instantiate an object of that subclass. Okay, so go back to your 41 or 40 textbook to remember all this stuff, but that's the idea of the base class. And then cat and dog, they're going to override stuff. So cat inherits from animal. To set the cat's name in the constructor, we'll just call the animal's constructor, and then we're going to override that talk method to say meow, and we'll give it a concrete implementation so that you can make cat objects. Same for dog. We're going to go and set the name of the dog through the animal constructor, and we'll also override that talk method to have something real and say woof, so that we can make dog objects. And so here are two animals. We have C and D. So cat's name will be Lonzo, and the dog's name will be Charlie, and then you can use them, of course. I'm going to make them on the heap, of course, as well, just to get some examples of that. We're going to make some shared pointers. Shared pointer to a cat on the heap, shared pointer to a dog on the heap. And remember, the beauty of inheritance is that you can treat things like their base class. So cats and dogs, you can put them together as long as you treat them like the thing they have in common. You can treat them as pointers to animal rather than just pointers to cats or dogs. So you can put them in a vector together, a vector of animal pointers, C and D, that's fine, that'll compile. And then when you iterate through this vector and you call like get name and talk, because talk is a virtual method, not a void method, because it's a virtual method, that means that it's going to pick the correct one. It's going to call, if it was the cat, it's going to call the cat talk method and say meow. If X happened to be the dog this time during this iteration, then it would pick the correct talk method for dogs and say woof. All right, so let's watch that happen. Bam. So Lonzo says meow, Charlie says woof, and all is right in the world. Okay, so that's just a simple example of inheritance. Make sure you understand this, because we're going to be using that a lot in this lab. I guess the new thing is, like, I'm making these things on the heap, but I'm using shared pointers to do it. So I'm including that memory header to make that happen. Okay, so for all intents and purposes, this is a cat star on the heap. This is a dog star on the heap. That's all it means to be a shared pointer. Okay, so that's that. And now I think we're ready to talk about the lab itself. Let's look at the write-up. So here we are in the write-up. So satisfiability solving. is what we're going to do. We're going to make a program that solves for satisfiability of formulas, and the shorthand name for that is SAT solving. SAT is short for satisfiability. So get the code, here it all is, and then you're going to implement the SAT solving stuff. All right, so let's see here. What do I want to say? Definitely read this whole thing. Please read this whole document. I'll give you the highlights though, and then we'll flip back and forth between this and the slides. So again, SAT solving is taking that Boolean formula, figuring out if it's satisfiable or not. So if you have this formula, it is satisfiable because there is an arrangement, there's an assignment of variables to values, which are Booleans, to make that formula true. There's many options for this particular one. What our goal is for this lab is to find every way to make this formula satisfiable, every way that makes it true. So we're going to try every single possibility. We have to generate every possibility. All right. So we got a bunch of files, logic.h and testlogic.cpp. We're making formulas. We're generating these formulas as trees. All right. And I'll show you that in a second. But formula is going to be the base class for them, and I'm building them in some functions. So let me show this to you. So let's go to the lab itself. So in logic.h, here's the lab files. In logic.h, I define a bunch of stuff, but here's the base class for our logical formulas. It's called formula. And what can you do to a formula? You can evaluate it under a mapping of variables to values, which are Booleans. All right. This will eventually make sense, and a formula gives back a bool at the end of the day. You can extract the variable names from a formula. We're going to need that later. And then we'll also have to deal with destructors potentially. So how do you make formulas? Well, an AND is a formula. You can AND together a left-hand side and a right-hand side. You can OR together a left-hand side and a right-hand side. These are all subclasses of formula. You can NOT an inner thing, an inner formula. And so we're just passing around pointers on the inside. And then finally, a variable is kind of like the base case. A variable is a formula itself, and it just has like the variable name inside of it. Okay, so that's the formula class and how it's arranged. And here's how you build formulas. Here's my test file for us. And if you scroll down to, I made some helper functions, but if you scroll down to like the first real test eval, this creates this formula in a normal way. So I'm making a bunch of variables for p, q, and r, and then I need to like take r and negate it. So I'm making a not on the heap, shared pointer to a not on the heap, and I'm passing around along into the constructor the inner thing, the variable r. So this has now made the not r formula, and then I can AND that with q by making an AND object on the heap, taking the q and passing the not r for the left and the right hand side of that AND. And then I can make the whole darn thing by taking the p on the left and the q and not r on the right and plopping them into an OR node. Okay, so we are making trees to represent formulas, and here's what they look like. All right, so for example, in blue, this is what this formula looks like: p, OR, q, and not r. Do you see how OR is the outermost operation? So you're going to make an OR node. They're really just trees. Okay. On the left is the variable p, on the right is this big AND, which has q on the left and then not r on the right. You see how not is another little tree with a subtree of the variable that it's negating, or just the formula in general that it's negating. Could be something large, but we're just making trees, okay? So we're just making trees, and our goal for the first part of the lab is to pretend somebody gave us a mapping of variables to values. Like, just pretend that p is true right now, q is false right now, and r is false right now. And our goal is to evaluate this formula under this mapping. Okay, and here I am in the test generating those mappings, like make p false, make q true, make r false. And so I have my formula, and I'm running its evaluation method and making sure, like, under these variables assignments, it better be giving back true, and then here's some new assignments, it better give back false in this case. Okay, so that's what's going on there. And so just stare at these files for a while. Eventually it will come to you, but it really is a tree at the end of the day. Like, this is the left side of the AND node, the right hand side of the subtree for the AND node. It's just smaller formulas. Same with OR. Left hand side, right hand side, smaller formulas that are being ORed together. That's what it represents. Okay? So somebody's given you You're always implementing this evaluation method for every kind of node in this tree, and you're given a mapping of variables to values. So it's going to end up being a tree traversal to evaluate this formula under a mapping of variables to values. And so you're going to make a recursive call to the left and a recursive call to the right. And do you see how those are smaller trees? You get to assume that it's going to give you back the right thing. What's your job as the OR node? Well, take the evaluation on the left and the evaluation on the right and OR them together. See that? So that's the goal. So to evaluate any non-var formula to either true or false, because you're given back a bool already, always, it's a Boolean expression, under that mapping for variables and values, then you need to recursively go down your subtrees. Maybe if you're a not, you have just a single subtree. So say you're at this OR. You're at this OR and you're ORing two things together, where x and y are some kind of formula. They're pointers to formulas. So to evaluate the whole OR, you better evaluate x and y, the two sides of that OR, recursively. And then you're getting a bool back for both of them. You get to assume it's going to do the right thing because of the recursion. It's a smaller tree. And then you can combine them back using just logical OR. Take this left side, take this right side, evaluate them both, and then OR the answer together. That's your answer for the OR evaluation. You see that? Smaller trees, just recursively evaluate, and then OR them together if you're in an OR node, and them together if you're in an AND node trying to evaluate. So you're implementing all these evaluation methods. Okay? And then eventually you're going to get down to variables. You're going to get down to variables where you're trying to evaluate a single variable. Like you're going to implement this evaluation method right here. How do you evaluate a single variable under this mapping of variables to values? Well, you just look yourself up in the mapping. You have a name. Go look yourself up in this mapping and see if see what value you're trying to pretend that you have. So like if you're trying to evaluate var p, then we're looking in this mapping and saying, oh yeah, just get back true, because that's what I'm assuming p is right now. Okay? So the leaves in this tree are always variables because that stops your computation. That's like when you replace something. A variable could hold anything. That could have been true or false for p, so we say which one it is. So we pass along that mapping, and it's the user's job to generate that entire mapping for every variable. You just keep passing along the same one during your evaluation, and when you get down to a var, you just look up yourself in the map. Okay? So you're going to override every evaluate method for every formula subclass. All right, let me try and draw that for you. So for example, here again is this tree that represents a formula. Go back to maybe the test file to try and understand again why it's working and like how it's constructing this giant formula as a tree. But this final node represents this entire formula, and you can think of it as this tree. All right, so here is P ORed with Q and not R. Do you see it? Do you see how that corresponds to this? And so you can make a formula. You can just like save it somewhere. Say call it F. Here's a color that we haven't used yet. Call it F. And the goal is you are going to, in your implementation, say you're going to evaluate this F. You're going to say f.evaluate, because every formula exists in the base class. Every formula needs to know how to evaluate itself down to a bool. Okay? So somebody's going to call f.evaluate on a given variable to value mapping, var to val. All right, someone's going to ask for that, and then you're going to kick off your recursion. So you have this mapping that you're going to just keep on passing along, and then if you're here, you're sitting at this OR node. That's what F is pointing to essentially right now. Every OR node has a left-hand side, go back to the code if you need to, and a right-hand side. That's like your left and right subtrees. All right, so you're going to recursively, the left-hand side and the right-hand side, those are formula stars. You're going to recursively, or shared pointers to formulas, you're going to recursively call evaluate on the left-hand side and the right-hand side, because every formula should know how to evaluate itself. And just you get to believe in the magic of recursion. Because this is a smaller tree, you can assume it's going to give back the right answer. This subtree, it's going to evaluate just P under this mapping, and, well, it'll give back true. You get to assume it's going to do the right thing. Assume this side gives back true, and then you get to also assume that this recursive call on this smaller tree gives back whatever Q and not R is, which happens to be false under this variable to value mapping. And so you get to assume that side gives back false. So the left-hand side, evaluating it, gives you back true. And the right-hand side gives you back false. And it's your job as the OR node to OR together both sides. That's how you compute a Boolean from your formula that lives with, no, from the formulas that would live within you that are being ORed together. So it's your job to just OR those two sides' answers back together, and you compute your final evaluated thing as true. That's what you give back. Under this mapping, this formula is true, and I hope you see why it's doing that. That's how the recursion is working, right? So let me kind of prove that to you some more if you need to be convinced. So like you try to evaluate the left-hand side, you hit the variable case. That's kind of the base case. Every variable is just going to look itself up in the mapping, and P evaluates to true, and that's the variable over here. So this subtree will totally give back true. You'll hit the variable evaluation method. And then this one, for an AND also has a left-hand side and a right-hand side. So again, you're going to recursively evaluate the left-hand side, just like for the OR. Recursively evaluate the left-hand side, which hits the base case for vars. It'll look up Q, and it will give back whatever Q is supposed to map to in the mapping. So we're pretending it's false here. And then you see this NOT node. That's the right-hand side. You're going to recursively evaluate that. And it's a NOT node, so it's also going to recurse. So it has an inner subtree, just one node though. And so it's going to go on and inside and evaluate that. It hits the base case, so what is R? It's supposed to be false. It'll give back false here. False. And then NOT just takes its inside, and what's it supposed to do with it? It's supposed to negate the answer. So NOT evaluated, like takes its inner subtree, evaluates it, and negates it. So its thing is true. Its answer is true for its evaluation. And now we've recursively evaluated the left and right-hand side of this AND. And what is an AND supposed to do to its two sides? It's got to take those answers and AND them together. So AND's final answer is false ANDed with true, which is of course false. And so that's why it gives back false to whoever called it, and it was that OR node asking for it. See that? So that was its parent in this tree that represents the formula. And so you got both of those things. Now you're ready to OR them together, and that's pretty much how it works. All right. So I hope that's making some sense to you and to your mind. And so once you make a formula, you can pass along this mapping, and your evaluation, your overloaded evaluation methods are going to make it all work. All right. So that's logic.cpp, where you're going to do everything in this lab. Definitely read all my comments. But here's some stuff that I've implemented for you. Like I've done that, extract all the var names. I've made all the constructors. But I've left the evaluation methods for you. So here, from here down, is stuff that you're going to be implementing. So like the AND evaluation method. What do you got to do? Go down both sides, recursively evaluate, and the answer. Or similar, not, also similar. Go down at the one child for the not, and then negate the answer for your final answer. And then for vars, remember that you got to just look yourself up. Okay? So that's the first part of this lab. And remember, the goal is to take a formula. Where was I going? To take a formula and find every way it can be true or false. So our goal is to represent formulas in code and be able to evaluate them. That's step one. Step two is to generate every possible var to val mapping under the sun, because we need to know exactly which ones make it true. Exactly which ones make that formula true. All right? So that's going to involve recursively doing some other things. Recursively trying every kind of possibility. Okay? So I think I'll just show you my racket example first. So here's kind of what you're going to do in code, but it's going to be a little bit different. You're gonna change my example and make it less generic. So let's pretend we have like a formula. We're trying to evaluate it, and that formula has three variables in it, x, y, and z. And let's say, just for sake of example, that they can all take on three values instead of the two. Like we know that in this lab it's supposed to be like x could be true or false, y can be true or false, z can be true or false. But let me show you something more general so that you can change it later. Let's say that every variable could be either set to A, B, or C, so one of three things, rather than just two. So this is a cool idea, and it scales to whatever you want it to scale to. So you can have every variable set to three things. And so here's how you print every possibility. Here's how you generate every possibility. You make a function, and you pass along two arguments. All right, two arguments. You're going to have a list or a set of variables that you have not picked values for yet, because you're eventually going to recursively pick them all. And then your second argument is going to be a list of variables and the choices you've made for them. So like you've picked a value that x should be, you've picked a value that y should be, and you're going to stick with them. And you're going to try and pick values for everything else that you have not picked values for. All right. So at the beginning of time, to kick off the recursion, you're going to call it like this function, where you're going to print all the possibilities of every variable, right, x, y, and z. So it's making a list of them in Racket. And you have made no choices for anybody yet, so your chosen vars list is empty. That's how you represent the empty list in Racket. Okay. Eventually, like, we're going to have two functions. This will just be a helper function in our final code, but this is good enough for us in this example. So here is possibilities.racket, and here's that function. So print possibilities. You have some variables to make choices for, and some variables that you've already chosen choices for. And your first call looks like this. So initially, at the beginning of time, everything is unchosen. You've made no choices for your variables, and nothing has been chosen yet. And the recursion, the magic of recursion, is going to try every possibility and make choices in every possible way. Isn't that cool? So let me just show this to you running. You'll watch it work. So Racket possibilities. And it really is going to try every possibility for x, y, and z, being a, b, and c in this example. So AAA, AAB, AAC, ABA, every one of the 9, 18, 27 possibilities, 3 cubed, right? 3 variables, 3 options for each variable. So all the way to CCC. It's really going to try and print out every possibility, and we want to do that same kind of generation in our lab. So here's how you do it. It's recursive. So I think the easiest thing to show you first would be the base case. So if we go back to the code, in the base case, you're here. The list of unchosen variables is empty. We've made choices for every single variable. We have nothing left to choose. So we've picked values for everybody, and recursively we're going to hit every option. But in the case where our unchosen variables list is empty, so we've made choices for everything, then we'll just print out our chosen variables or use them in the way that we need to use them in our lab, like we'll use it to evaluate our formula. So that's your base case. You've got nothing left to choose, so you've made choices for everybody, and recursively you're going to get down to this base case a bunch of different times because there's a bunch of different possibilities. All right, so that's your base case. Your recursive case is when you still have at least one variable left to make choices for. So like you've got your chosen vars, and you've made some choices already perhaps, and you still have at least one variable up in here that you have not picked a value for. And so you're going to recursively try them all. Okay, so your unchosen vars is non-empty, and so what you're going to do is you're going to take one variable out of here, like maybe the first one, maybe it's x or y or something. Take the first one out, and then get rid of it. So make a list of everything but that one, because that's going to be what you use in recursion. So, and then you're going to make a recursive call for every time you need to make a choice, for every option. You're going to recursively pick one option, and then recursively pick another, and recursively pick a third option, and so that gives you all the different ways it could have happened, and so it'll recursively end up trying every single possible option in the end. All right, so here I am printing the possibilities of every variable except for the one I just picked, right? Every variable, not including the one I took out, and I've now made a new choice. So I have some chosen variables already, maybe. I'm going to add to that choices list. I'm going to set that variable in this first recursive call. Let's pretend that it's A. So that's me trying the possibility that that variable is set to A. And then here are my two other recursive calls. Try it set to B among all the other choices. Try it set to C among all the other choices. And then like get rid of those other variables out of there. All right. Make sure it's not, it's one less thing in this list of unchosen variables at this point when I'm making this recursive call. Okay, do you kind of see how that's working? So you just slowly but surely add to your chosen vars list, pick a choice for each of these variables, and eventually it'll be one smaller, one smaller, one smaller until it's empty, and we've tried them all and we've seen all these possibilities printed out. Okay, so kind of hopefully you see how the recursion is working. That's the goal, and this is what you're going to implement in your lab. It's just for every variable, you're going to not make it be A, B, and C. You're going to just make it be true or false. Okay, that's how you're going to build up your list of options. But just in case it's a little confusing why this is working still, let me try and draw it for you. So at the very beginning of time, your first recursive call looks like this. And say that P stands for print possibilities. Your very first recursive call is going to have everything unchosen, right? Everything unchosen and nothing chosen yet. That's our first call. everything unchosen and nothing chosen. And then we're going to hit the recursive case. We're going to plop something out. We're going to take the x out. That's the first thing. And we're going to make a choice for x. And recursively make every possible choice for x. We're going to make the recursive calls where x is set to A, x is set to B, and x is set to C. And we're going to recursively try the other options for, try every other option for y and z. That's every variable that's left after taking out x. So that's what is going to be called here. That's what these three calls are trying to do. All right, so hopefully that makes a little bit more sense drawn out like that. And then, of course, all of these are going to run. Like here's the left recursive call. The rest of these are just as wide and just as deep. I just can't put them all on one slide. But do you kind of see how it's going to end up trying everything? And so under this recursive call, we're going to hit the recursive case. We're going to plop out the y. Now that we want to we see that we still have a variable left to choose for, so we're going to take the y out and make a choice for it. We're going to keep the x set to A in all of these options, and now it's y going to have that's going to have every possibility accounted for. So we're going to set y to A in this recursive call, y to B in this recursive call, y to C in this recursive call. Because I'm making 3 recursive calls, it's going to try every possibility. You see how that's going to become a very large recursion tree, but eventually it's going to hit base cases, and that's why it's trying every option in the long run. So again, like here's that left recursive call, and this one is again just going to be it's going to be as long as the other ones. I just can't put them all on one slide. So you see how it's trying everybody. And then finally, this is the last recursive case. We see that there's z. That is one variable that still needs to be chosen for, and so we're going to take it out of the chosen variables, and we're going to take whatever was already there, x being set to A and y being set to A. We're going to keep all those there. That's still our choices list. And we're going to plop on that z could be what options. We could have z set to A, z set to B, and z set to C, and this is finally our base case. Now we have nothing left to choose. We've made choices for everybody, and do you see how like we're going to end up making every possible choice in the long run given the way that the recursion's working. And so once you hit the base case, just like print this out. That's one option. Print this out. It's another option. Print this out. It's your third option. So like that is why you see all this fun stuff. And this is also why you see that exact order as well, because we're doing A first, then B, then C, if that makes enough sense. So this is a good picture to understand what's going on. And so you're going to modify this algorithm to set things to not A and B and C, but to true and false. Okay, so it's going to be a little bit smaller, less work being done at each recursive case. So that's what you're going to do in code, and you're going to do it in 2 functions. There's satsolve and satsolve helper. This one that I just this trying all possibilities, this recursive one, that's your helper, satsolve helper. All right, so we'll go there and talk about it in a second. But yeah, these are the 2 functions that actually do the satisfiability checking. You're going to try every combination of values there, and you're going to save every combination of values that evaluated to true, because that's your goal. You're trying to find every way to make this stuff true. So here is logic.h. And so down at the bottom here we have our 2 functions. We have satsolve, takes a formula, and it gives back every mapping of variables to booleans that makes this formula true. All right, we're giving back every one of them, a set of these mappings, every one that works out. All right, and it's this helper function that's recursive that actually makes this happen, that actually does the hard work. So it's going to take the formula you're trying to solve for. This is your set of unchosen things, all the variables you have not made choices for. And then here's the choices you've made so far. You're building up a mapping of variables to Boolean values. And then you're passing along as a reference, see this reference sign? You're passing along as a reference your satisfying solutions, and you're going to just add to it every time you find a new one in the base case when you've made choices for every variable. All right? Hopefully it's slowly coming together in your mind. I've made some more comments for you in the CPP file. But here's satsolve, and its job is to just like make a list, make an empty set of solutions, and eventually return that, and in between call the helper function with the correct initial values, where like everything is unchosen and nothing is chosen. Okay, that's the idea. And then here is satsolve helper. I have written a ton of comments. Please read them all. But you have the formula, you have a set of remaining variables left to make choices for, you've made some choices already, and then here's all your satisfying solutions. You're going to add to them every time you find a new one. All right. So just like the racket example, in your base case, you've made choices for everybody. In our lab, that means we have choices for vars is complete. It has every variable chosen for. And so you have a var to val mapping that you can use, and now you should see if it works for your formula. Evaluate f under that mapping, and if it matches, if it works out, add it to the satisfying solutions. Otherwise, forget about it. Return. Otherwise, you're in the recursive case. You still have some variables left to make choices for. You don't have a full mapping yet. And so pick one out. Take the first one, let's say. Begin would work out. And then get the rest of them, because that's what you're going to pass along as those remaining vars set for your recursive calls. And then you're going to make 2 recursive calls, just like I made 3 in the racket example, because there's only 2 values that you want to try. You want to try true and false. So you're going to make the recursive call for the formula f under the new smaller remaining vars, under the bigger choices, with those same satisfying solutions, because you're going to set that next choice set to true. So you're going to make a choice there for that variable you just extracted. And then you're going to make another choice and recursively try it with that next choice variable set to false instead of true this time. And so this is going to be how you eventually end up trying every option in the base case. And you're just going to save every satisfying solution that you find, and that'll be that. Okay? So that is essentially your lab. Hopefully that made enough sense. So again, like in the base case, you've made all these choices. In the recursive case, you're still trying to make every choice, and so you need to make 2 recursive calls. And eventually you'll get down to base cases. So yeah, just read all this stuff. It's really helpful. Read all the comments. I don't want to just read them back to you. Definitely do all that. And then finally, in the testing file, which by the way, you'll use this make file that I gave you to compile it and then run it like this. In this testing file, in addition to evaluation tests, I have like sat-solve tests. So here we go. Like here I am making a simple formula that's just a variable, and I'm sat-solving it. Here I am making a larger formula. It's not P ORed with Q. See how I'm reading that? And then here's a bigger formula. I'm sat-solving that, finding all the solutions, and I'm printing them out. Sat-solving this larger formula with even more variables, sat-solving it, and printing all the solutions. And so I've made a file that you can compare your output to. This is called expectedoutput.txt. This is what you should see when you run the test. You should see the first evaluation one's passing, and then here it is printing out the solutions in a nice order for every other formula. Like here's the sat-solve test one. There's only one way to make that true, just set P to true. For this other test, it's like set P to false and Q to false, it'll be true. Set P to false and Q to true, it'll be true. Set P to true and Q to true, it will also make it true. There's 3 satisfying solutions for that formula, 2 satisfying solutions for this other next formula with 3 variables, and then for test 3 with 6 variables involved, there's a lot of options to make it true. There are apparently exactly 61 of them. And so this is the output that you want to see that you can compare your answers against. And this is what the autograder is going to be checking for. All right, so you can compare your output of this test logic file with the expected output to see if it's all working. And then once you're done, the only file that you have messed with is logic.cpp. So that's the only one you're turning in. The autograder is using the default values of every other file. All right, so please don't make any changes to any other files. Just only do your changes in logic.cpp, since that's what you'll be turning in. And yeah, once you got it all working and passing, that's just turn in that one file. And there's the rubric. Make sure to check your grade, and just remember to start early, please. So I think that's everything that I wanted to say about the lab. Just watch the due date. Make sure that you get it in before then, and yell at me if you have any questions. So again, good news and bad news. It is a very short lab in terms of writing code. Once you wrap your mind around everything, there are a lot of moving parts. So please start early. And then the bad news is that there are a lot of moving parts. So there's a lot of stuff that you got to review from CSCI 41, etc. And some new ideas, like this is just trees at the end of the day, but we're doing something really cool with them. So you just have to wrap your mind around it. And it will be very satisfying, I guess pun intended, to get this all working. And I wish you luck. And so let me know if you have any questions, and I will see you later.